Well, thank you very much, Giovanni, for this great workshop. It's really good to have some fresh data, some fresh discussion. It is very nice. I mean, can you guys hear me properly?
Yeah, absolutely.
Sure. Yes.
Okay, fantastic. So, I mean, the title on the website of my talk was about the strategies to enhance the skyrmion mobility, and I expanded a little bit the scope to talk also about a bit of DMI because we did some nice work on two-dimensional magnets. So I wanted also to share a bit about that. So I will start with talking about the mobilities of magnetic skyrmions. And basically, when we started to work on that, we wanted to to see if there were ways that we could contribute to this very intense and very competitive field. And try to find some smart manners to make the skyrmion goes faster. And basically, as far as I understand, there are two main issues for the skyrmion mobility. The first one is, of course, the Hall effect, the fact that the skyrmion is not following the electron direction, but is actually going by on the side, and that we have already heard some very nice talks about that. So we just move on quickly to the other limiting factor, which is, of course, scattering of the skyrmions against the grand boundaries. And although they are supposedly topologically protected, well, there's just so much you can do. And when your sample is polycrystalline, well, you actually start having some very difficult trajectories. I mean, this is not just straight; it actually scatters all around. And we wanted, what we're gonna, I mean, I'm gonna talk about that in a minute. We actually realized that skyrmion Hall effect, together with scattering against the grand boundaries, makes actually the mobility even worse. So, so basically, the perspective I'm going to take to try to enhance the mobility of skyrmions is to try to take advantage of the topological currents that flow in a skyrmion. We actually started to work on that, inspired by a collaboration with Matthias Klaue in 2000. We actually started in 2013, if I remember well. And basically, they were looking at the resonant motion of magnetic vortices. And this at that time, before the skyrmions took over, one of the big questions was to understand why vortices display a much larger non-adiabaticity compared to linear, one-dimensional domain walls in the same kind of material. And what we realized is that this enhanced mobility, what is happening? This enhanced non-adiabaticity is related to the topological currents that flow in non-trivial topological objects. So here I'm just taking the case of a vortex, but it works the same with skyrmions. So we know that when we send a current of electron through this kind of topological object, the trajectory of the electrons is bent, and basically they are reoriented, and they experience a Hall effect, essentially, that is called the topological Hall effect. And as a reaction, your skyrmion or your vortex will also be pushed on the side. Okay, so essentially the skyrmion Hall effect or the vortex Hall effect is directly related to the topological Hall effect experienced by the electrons flowing in this structure. And from a theoretical point of view, you can actually show that when you have a moving magnetic texture, the electrons that are flowing through this texture experience a spin motive force, so an electromagnetic field. Well, I would say an electric field and a magnetic field that are both spin dependent, and that depends on the spatial gradient of the magnetization as well as on the time dependence of the magnetization. So these are aspects that were studied, I would say, probably a decade ago or something like that. And what we realized is that actually the emerging magnetic field experienced by the flowing electrons has a dramatic impact on the spin torque experience that those electrons exert on the skyrmion or on the vortex. I mean, from this point of view, this is completely equivalent. So because of this time-dependent and spatial-dependent magnetic texture, you can define this spin-dependent electromagnetic field, this E and B here, and then you can redefine the spin current or the spin-dependent charge current flowing through the system And of course, you have just Ohm's law. I mean, some very simple. I mean, Joule's law. Sorry, some very simple connection between the electric field that you apply and the current that you're gonna measure. But also the fact that you have some spin motif force. The spin motif force will also generate some current that will then depend on the time dependence of the magnetic texture. And you have actually also a Hall effect that is coming from the fact that there is an emerging magnetic field. So this term here is nothing but the topological Hall effect. What is interesting though, that when you have a moving skyrmions, then you're gonna have an interplay between the spin motif force and the emerging magnetic field that will give you this fourth term here. And what we're gonna try to do is to explore this fourth term. So now we have a spin dependent current. I mean, the spin polarization of this current is aligned along the magnetization, the local magnetization. We are in the adiabatic limit. And if you take the gradient, the local gradient, the local divergence, sorry, of this spin-dependent current, then you can define a torque. And I would say the first term here would just give you the regular adiabatic torque. The second term, the third, let me see, 1, 2, 3. Yeah, the second term here will give you the non-local damping. And the last term here, that's the interesting part. That actually does. Sorry, this term here, I'm sorry, the third term here will give you what we call the non-local non-adiabaticity. The trajectory of the electron is modified due to the topological Hall effect. So you end up having a transverse spin current going through the structure, and this transverse spin current will also exert a torque on the skyrmion. Now, the reason it's interesting is because if you see that this is proportional to the derivative, to a special derivative of the skyrmion. It's actually at the second order. It's dm over dx cross dm over dy. So it means that the smaller the skyrmion, or the smaller the vortex, of course, the larger this term here. So now we have a mechanism that enhances the non-adiabaticity when the skyrmion gets smaller. So we did some analytical theory. So of course, it's not as good as macromagnetic simulations, but it gives you some good ideas. And we can get the longitudinal velocity and the transverse velocity of the, this is in the case of a skyrmion, isolated skyrmions, as a function of the electron drift velocity. So this is very well known, and I'm sure this community is very familiar with those formulas. And what we show that when you have this electromagnetic field, this emergent electromagnetic field taken into account, then well, you have this effect. You have an effective damping, an effective geometric ratio, and an effective non-adiabaticity term. And basically, all those terms depend, I mean, are inversely proportional to the square of the radius of the skyrmion. So what it means is that the smaller the skyrmion, the larger those terms. So well, this eta parameter here is actually mostly 1. I mean, it only becomes, I mean, it only increases for very, very small skyrmions. So I would say this one can be neglected. But if you look at the effective beta parameter and effective damping, then you see that this is, the correction is proportional to 1 over the square of the radius. So if you have a smaller skyrmion, then this skyrmion will experience both enhanced damping as well as enhanced non-adiabaticity. So in this case, you're going to have a much larger Hall effect. So the small skyrmion, at least in this limit, so there is no disorder in this theory, the smaller the skyrmion, the larger the non-adiabaticity and the larger the Hall effect. So of course, this is something you would like to avoid. So that's one aspect. And I think this is actually very detrimental, of course, to the mobility. So I'm going to show in a couple of minutes what we propose to try to actually take advantage of this enhancement. Now, the other issue we have is, of course, the grain boundaries, because all those materials we are dealing with are usually spattered, so we have a lot of grains. And what we realized is that when you send a skyrmion through this kind of system, depending on the strength of the electric field that you apply through the system, this skyrmion will experience a sliding motion. So this is a micromagnetic simulation that was done by one of my former postdoc, Akshay Salimat. And so essentially it models the motion of this skyrmion here in a polycrystalline sample. And if you have a small driving current, well, then the skyrmion cannot go through the boundary, and it basically slides against the boundary. You have a sliding motion here. Now, if you increase the currents, then you will still have some sliding motion here, and this is essentially where the skyrmion is going. And well, if you really want to get rid of this sliding motion, then well, you have to really inject a large current density. So I think this is an interesting aspect because it really shows that polycrystallinity enhances the Hall effect. So it's basically even more detrimental to the mobility, because some of your skyrmion will basically tend to go on the side rather than going straight, and that would be enhanced by the polycrystallinity. So of course, this effect depends on the ratio between the average size of the grain on the skyrmion size. So if you have a very large skyrmion, and this is something that the previous speaker mentioned, then of course it covered the full. It will basically be less affected by this effect. Another interesting aspect is the fact that there is actually an overshoot when you want to deepen the skyrmion. So if you start with let's just focus on this one here, on the last slide here. If you have a skyrmion that is spin on small grains, and you will try to deepen the skyrmion, then the Hall effect shows, so this is the transverse velocity here, shows an overshoot close to the threshold. Of course, all these aspects are interesting, but they are very detrimental to the mobility of those skyrmions. So what we proposed was actually to take a wire. If you have a wire, and basically you would try to cancel the transverse velocity. And when you move a skyrmion through the wire, what we find is that just by moving the skyrmion, we will be able to pump a charge current through the system. And this is really due to the fact that you have this electromagnetic field that is accompanying the motion of the skyrmion. So it's very similar to the spin motive force you have in magnetic domain walls. I mean, there are a few very important differences, but I don't want to enter in details here. But in these simulations here, so it's a time-dependent quantum simulation. We have a wire, we have a skyrmion, we just move the skyrmion. And what you can see that in all those snapshots, you can actually build up a longitudinal charge current flowing through the system. So you can actually measure, so can put some probes along the wire and just measure the current that you can pump through the wire. And this is an interesting aspect because you could imagine to have a train of skyrmions. If you have a train of skyrmions here through the wire, and you start moving one of those skyrmions, then the first skyrmion would actually pump a charge current to the second skyrmion, which would enhance the torque. So basically, you will end up having, if you have a chain of skyrmion, you would having a collective effect where each skyrmion pumps a charge current into the next skyrmion. So at the end of the day, you have an enhance of the global mobility of your skyrmion train. So that actually is something that would be very interesting to see experimentally. So I know that there's a lot of experimentalists in this audience, so that would be really nice to see if this is actually reasonable. Another strategy to enhance the skyrmion mobility is, of course, to use anti-ferromagnetic skyrmions, because as we know pretty well, then there is no anomalous Hall effect. There is no skyrmion Hall effect because the two sublattices compensate each other. And in this case, all the non-adiabaticity is converted into a longitudinal velocity. So in this case, you could think, well, if my non-adiabatic torque increases when I reduce the size of my skyrmion, then if I take an anti-ferromagnetic skyrmion, then the mobility of my anti-ferromagnetic skyrmion should increase if I shrink the anti-ferromagnetic skyrmion. And this is something that I would say it's a fairly naive idea. And that's so that's actually what we proposed a couple of years ago. And if you actually do some simple soft mode calculation, it actually works pretty well. And the non-adiabatic torque is increased when the skyrmion shrinks size. The problem is that if you actually enter that into a micromagnetic simulation, it doesn't work anymore. Because the problem is that the skyrmion is not rigid. And what we realize is that, and this is a nice work by Gina and co-workers, if you have an anti-ferromagnetic skyrmion and you just try to push it with actually spin hole torque or just non-adiabatic torque, the skyrmion will actually start to exhibit a lateral expansion. And this is something you can, I mean, you can actually do some analytical calculation and demonstrate that the lateral, I would say the lateral expansion is connected to the longitudinal expansion of the skyrmion. And this is really a reminiscence from the Lorentz invariance that is embedded in the anti-ferromagnetic LLG equation. So the problem is that means that if you try to push your anti-ferromagnetic skyrmion, your anti-ferromagnetic skyrmion will get elongated. And there's a point where it will reach the walls of your nanowire and annihilate. So the question is, well, is there any particular torque that will, or any particular situation that will avoid this lateral expansion? So what we did is that we studied two different effects, and this is a collaboration with Giovanni and Ricardo. So they implemented the topological torque, the one I was just mentioning, those topological currents flowing in the skyrmion. So this is this picture here. So we're going to compare the topological torque with the regular spin hole torque, the one that is usually used in experiments, and see how the skyrmion behaves under those two torques. So I'm just putting the main results here. So on the left side, you have the spin hole torque and the actual velocity that you can get. And what you can see, of course, that the larger the current you send in the system, the larger the lateral expansion. And there's, of course, here is you have the lateral expansion of the skyrmion as a function of the current velocity. And you have this very strong quadratic expansion that diverges, of course, when you reach the spin wave velocity. And there's a point where the lateral expansion of the skyrmion is too large, and the skyrmion annihilates because it reaches the boundaries of your wire. So it can go very fast at large current density, but it gets annihilated. Now, if you look at the topological torque, so now we assume that we just send the current inside the magnetic wire itself. We just take advantage of these topological currents. In this case, what you see that the velocity saturates at much smaller current density. And this is really because the topological torque depends, basically increases when you, well, I would say reduces when you enhance the size of the skyrmion. So you send a current through the system, you move the skyrmion starts getting elongated, but the larger it gets, the less topological torque you have. So there's a kind of self-compensation. So you actually start saturating the velocity of the skyrmion way before you reach the higher limit of the spin wave velocity. And in this case, of course, correspondingly, the expansion gets slowed down. So then you go from a quadratic expansion to a linear expansion, which is, of course, way more controllable. So I think that that's the main message of this discussion. It's that there's really a trade-off between large velocity and skyrmion expansion in antiferromagnets. So that's for the skyrmion part. I mean, yeah, for the skyrmion mobility part. Now I would like to move on. Let me see. I still have a few more minutes. I'd like to move on to the Dzyaloshinskii-Moriya part because I think that would be very interesting for this community. We have studied Dzyaloshinskii-Moriya in two-dimensional magnetic materials. I'm going to show you two important results. What I think is quite exciting. The first one is on the Janus, what we call the Janus transition metal dichalcogenide monolayers. So you have probably, I'm sure you're all aware of all this, the burst in two-dimensional materials, especially magnetic two-dimensional materials. So there's a lot of debate, but let's put the debates on the side and just look at the physics of the spin-orbit physics of those systems. So what we do is that we take vanadium dichalcogenide. So the kind of system we have is vanadium here, and we have chalcogens on each side. So experimentally, what you can get is vanadium diselenide, vanadium disulfide, and so on. What has been shown in my previous university in KAUST is that it's possible to actually desymmetrize this kind of two-dimensional system and replace one chalcogen by another. So what you have here, I mean, the kind of system we study is vanadium embedded between selenide below and tellurium above. And what we get is, well, I mean, of course, we did some density functional theory calculations. So I will probably go, I will probably just spare you with all these details. But what is, I think, quite interesting is that because there is a dissymmetry between the tellurium and the selenium elements, we can create strong orbital moments perpendicular to the plane. And of course, we expect to have some strong Rashba spin-orbit coupling. So if you actually calculate the band structure, and you project it on the spin momentum, you can get some nice Rashba-like spin texture in momentum space. You can also show that this spin texture is larger. This spin momentum locking is larger in the case of selenium tellurium. It's decent for sulfur tellurium, but it's much larger for selenium tellurium. So that's our star material. We can show that this is coming from the coupling between the dz square orbitals with the pz orbitals of the chalcogen. Actually, it's more like the pz of selenium is coupled to the dz square of vanadium, and that creates a strong Rashba spin-orbit coupling. So if we have Rashba, of course we have Rashba torque. So we just play with that. And if we have Rashba torque, we have Dzyaloshinskii-Moriya, and that's the interesting part for us. So to calculate the Dzyaloshinskii-Moriya in these systems, what we do is that we follow a procedure that was put forward by Stefan Blugel's group in Univ. So we create spin spirals in momentum space, and then calculate the spin orbit energy at the first order in spin orbit. So this is the kind of of energy dispersion we get. We calculate this energy dispersion with spin orbit coupling, without spin orbit coupling. We make a difference. And then we get the anti-symmetric dispersion, which is really the hallmark of Dzyaloshinskii-Moriya. So we get those curves for what we call the Néel out-of-plane spin spiral. So this kind of Dzyaloshinskii-Moriya is really the one you would have at interfaces. Okay, it's really coming from the fact that you have Rashba plus magnetism. So it's very, I would say, all this physics is well known. And what is interesting is that you actually have some fairly decent Rashba strength. If you look at this one, 5.7 electron volts angstrom per unit cell. This is fairly similar to what you would have. It's a bit smaller than platinum, but this is fairly decent. So what we did is that we took those parameters from density functional theory, and we ran some atomistic spin simulation as a function for different temperature, and tried to build up the full phase diagram of those systems. An issue we have, though, is that vanadium diselenide and vanadium selenide tellurium has planar anisotropy. It's like an easy plane material, so it could actually be interesting for spin superfluidity, but not for metastable skyrmions. So you can still get some bimeron lattices on skyrmion lattices, but you need a strong magnetic field, either in plane or out of plane. So we were able to build the full phase diagram of the systems. And essentially for, I would say, decent external magnetic field, you can get some bimeron crystal and a skyrmion crystal, depending on the kind of system you want to look at. Giovanni, do I still have 2 minutes? Or not?
1 minute. 1
minute. Okay. So then I will try to open this. Yeah. Okay. I will start. I will finish with an opening. So I'm pretty sure you're all aware of the recent results. I'm just showing one of them that reports the observation of skyrmion lattices in iron 3 germanium tellurium 2 bulk system. So these are van der Waals materials. So you have layers of this iron germanium tellurium system. And so we have been trying to understand where those skyrmions are coming from, because it look like Néel type skyrmions, if I'm not mistaken. And we really didn't really get why you could get those kind of skyrmions in such thick materials. So what we did that we just took one monolayer of this iron germanium tellurium, because it's much easier than the bulk, and try to understand what's happening there. And what is interesting that well, this system is non-central symmetric, so you could imagine to have some skyrmion there, but when you analyze the symmetry, it actually doesn't work. You do not get a Néel-like I mean, do you know the Dzyaloshinskii-Moriya that would stabilize Néel skyrmions? And so I will go quite fast here because I don't have much time now. I probably have 10 seconds left. So if you actually look at, there's a mistake here, it's 6 bar M2. If you actually look at this, the point group of this system and analyze it, let me move on there. What Arne Bratas and his students have shown is that you can get some very interesting current-driven anisotropy, which is essentially a damping torque. It's not a damping torque. It's well, let's call it a damping torque because it's even in magnetization. But you can actually get a torque with these very peculiar, very strange symmetries. What is interesting is that in the long-range limit, the damping torque on the Dzyaloshinskii-Moriya interaction have the same symmetries in the long-range limit only. So then you can use this kind of procedure and compute the Dzyaloshinskii-Moriya tensor. So we get this kind of tensor here. And if I rewrite it in the continuous limit, I'm going to have this kind of total derivative. And you see that it's not the regular Dzyaloshinskii-Moriya you would have at interface. It's something that is a bit more strange. And if you analyze that, you realize that you cannot stabilize anything interesting there, not in the long-range limit, at least. So that's just for the continuous limit. Now, what we did is, of course, calculate. So we took the same system and we calculated the Dzyaloshinskii-Moriya interaction using the spin spiral, the generalized block theorem from the Ulis group. And we did it for the Néel type in plane, the blocks type spin spiral, and the Néel type out of plane spin spiral. And what is interesting that we got Dzyaloshinskii-Moriya only along one particular direction of the crystal, so the gamma K direction. And we only got it for the Néel in-plane spin spiral. Okay, so the Néel out-of-plane spin spiral, which is the one that should reveal the interfacial kind of Dzyaloshinskii-Moriya interaction. This out-of-plane Néel spin spiral doesn't give you any Dzyaloshinskii-Moriya, only for the in-plane spin spiral. So we can actually analyze that a little bit further, but I will spare you with all those details. I just give you some hands-waving arguments. So if you take the gamma M direction, which corresponds to this direction in real space, what you see that there is a mirror symmetry here. So basically electron jumping from one, so this is your iron atom in the middle of the sample. So if you jump from this iron atom to this one here, you see that the path that you visit, the chemical environment across this path is exactly the same as if you go counterclockwise. Okay, so the clockwise and counterclockwise path compensate each other. There is no Dzyaloshinskii-Moriya. Everything is fine. So there cannot be any Dzyaloshinskii-Moriya for spin spiral along this direction. But if you take, let's say, those equivalent directions here, which corresponds to the gamma K direction in momentum space, then you see that in this case, the clockwise and counterclockwise path visit different chemical environment. So then they do not compensate each other, and you expect to have a decent Dzyaloshinskii-Moriya interaction only in those directions. Now, there's something else that is quite interesting, is that if you go for the next nearest neighbor, so let's say this is only for the nearest neighbor Dzyaloshinskii-Moriya. Now, if you go for the next nearest neighbor Dzyaloshinskii-Moriya, then you see that the environment is inverted. Okay, you first go through the blue atom for the clockwise direction, and for the red atom for the counterclockwise direction. So there's a kind of compensation on the long range. So you can actually generalize this idea to the third neighbor, fourth neighbor, and so on. So basically, on the long range, the Dzyaloshinskii-Moriya vanishes, and this is what we concluded from the continuous model that I showed in a couple of slides ago. So it actually means that, just to sum up, we have Dzyaloshinskii-Moriya along the gamma K direction. There's a compensation between the higher order DMIs, which means that there is no DMI on the long range on the long range limit. But there is a DMI that stabilizes Néel in-plane spin spiral on the short range. And so this is the kind of spin spiral you would expect. Okay, you would have a spin spiral in the plane turning this way. Now the problem is that we have a very strong perpendicular anisotropy, so we need some surface engineering to try to cancel it and have a real in-plane spin spiral. But I think this is actually quite an interesting perspective for experiments. So that concludes my discussion, my presentation. I'd like to, of course, thank the guys who actually did the work. Yeah, so I have moved to Marseille, as Giovanni was mentioning it. So there are postdocs and PhD positions available. So please apply. Thank you very much.